Hello, everyone. Welcome to the final session of the day. And today I get to talk to you about the magic of music matching. So I'm going to take you on a little journey back. First, some information about me, not very important. I do stuff with Java, and I own a company called Open Value. And you can find me online if you have any questions after the presentation. Back to the story. Why did I go into programming when I was younger? Well, for me, it was basically to play games. So the first time I actually learned to program was using one of these books. And these books, I just got them from the library, went home, started up the computer of my father, and I was able to write some code, which was literally in the book. And all these typos I made, basically, if you did everything well, then everything compiled and you could play a game. But every little typo you made or every mistake forced me to actually learn a little bit more about programming each time. And this is my first, the first time I actually saw code and I saw what it does and how things worked. And this gave me some understanding on how you would write a program, how you could make something move on a screen, how you could process text, for example. But there are always things, programs you use, apps you see, which are just like, they feel like magic moments. And I wanted to understand how everything works. So some of the magic moments I had was the first time I, instead of having purely a text-based game, to something that has images in it. So, or for example, when you navigated a 3D world, the first time I fired up something like Duke Nukem or Quake or those kinds of games. I had no idea how you would program that, how you could create a 3D world using just code. The first time my computer spoke to me, I was like, how does this work? How can my computer speak with a human voice? Like, that, no idea how it works. Now I know how it works, but back then I wanted to find out. I wanted to do that myself. Was there some kind of command that I could give it text and it would speak to me? Well, it turns out that wasn't the case back then. Back then it was just like wave files that were being played, but now we can do these things using Alexa or Google Assistant. The first time you used OCR, you took a digital picture of something, or you put it through the scanner, and it recognized not only that it's an image and there is some text on it, but actually you could select the text, and it actually understands. You could search documents. Like, that was another magical moment for me. And I needed to know, how does that work? How can I create something like that? Voice recognition, same thing. Like, how does my computer understand when I speak to it? Google Earth, like the first time you see your own home on something like Google Earth, that's really magical feeling. And one of the last times I had this was actually when I fired up Shazam for the first time, or actually when a friend of mine showed me Shazam. And this, the first time I saw this was in my hometown, Maasluis, in the Netherlands, and I was in a pub, and it was the summer of 2010. And my friend came up to me while we were having a beer on Friday evening, very late. There was music playing. And he said, "Hey, Roy, look at this app." And he had Shazam installed. So he put his phone up in the air. He pressed the big button in the middle. And the phone listened for a little while. And then the phone told me which song was playing at that particular moment in time in the pub. I was flabbergasted. Like, my mind was blown. I had no idea how you could write a program that does something like that. In 2010, I was probably a professional programmer for 5 years or something. I could make official bank programs and other stuff and forms. But how you would make an app like this? No idea. So the next morning, about 10:30, I finally woke up, a little bit hungover. But I needed to know, how does this application work? How does Shazam work? Back then I didn't have kids yet. I did have a girlfriend, but yeah, whatever. My entire weekend was free. So I set myself a goal. Before the end of the weekend, I have to know how this works. How can you possibly create something like this? So I'm a Java programmer. So the first thing I did was Googling Java. How do you actually listen to a microphone? It's like, I've got this microphone here. I can speak in it. And how can I use my programming skills, my code, to get information from this? And it turns out in Java, it's actually pretty easy. Same with JavaScript. There are just APIs and you can access the microphone. And in case of Java, you just have to give it an audio format, and it has stuff like a sample rate, which means how often does it listen or detect something. The sample size, in this case, 8 bits. So how big is the thing that it measures? How many channels does it have? Is it one microphone or is it 2 microphones? Well, I obviously only have 1 microphone. And the data we get, is it signed and is it big or little endian? So we give it some audio format. And this is basically the same in any other programming language. You have to specify these things when you open a line to the microphone. And that's what I did next. In Java, you have this built-in target data line class, and this actually opens a line to your microphone, and it takes care of all the hardware stuff. And after that, you call audiosystem.getLine, and you get data. And this data is just a series of bytes. So I made a for loop, and while it's running, I store everything in a byte array, basically. So by now I was maybe 1.5 hours later, getting ready for breakfast, did some programming. I accessed the microphone. I got all this byte array data. So I was feeling very well. I was like, yeah, I woke up, which was one thing. I accessed the microphone and I'm already getting all the data. So now I just need to match it and tell the audio or tell the user of the app like what the song is. So I thought, well, that's the easy part, right? Getting access to the microphone is the hard part. So then I decided to take a look at the data. What is actually in this byte array? Maybe the name of the song is already there, or you get some MP3 file, or what do you get when you access a microphone? And I got something like this in the byte array. And then I realized I actually have no idea how microphones work, or what kind of data you actually get when you access the microphone, or what these numbers even mean. Like is this, what is sound? Like my whole world collapsed. I had no idea. So what I did is I decided to take these numbers and plot it in Excel and create a graph. And when I did that, I got something like this. And when I recorded myself and it was silent, the line was almost flat. And when I made sound, it went up and down. So I thought, yeah, I've seen this before. If you have sound editors, then you get this graph thingy. But still, I had no idea what these numbers mean. Like, what? Yeah, I know this is sound, and I know when you're silent, there's nothing, and when you make noise, there is a thing. But what is this thing that there is? Like, I don't know. Turns out, if you want to know that, then you need to know a little bit about biology and physics, because sound is actually pressure. So when I make a sound, when I clap in my hands or something, it's the air molecules are moving. And this is actually a pressure wave. So I'm talking to you, and my voice is making these pressure waves. Your ear has a small membrane in it, and a small eardrum behind that. And these pressure waves are actually moving the membrane in your ear, and that's what we interpret as sound. And it turns out the microphone I'm actually using right now to speak to you all, is using exactly the same thing. There's a small membrane in it, and it vibrates. And instead of having a small hammer that's wired up into your brain, there's a small electrical circuit attached to this hammer, and you actually measure the position of this membrane over time. So that's what these numbers mean. These numbers are nothing else than just the movement of this little membrane. And now it all starts to make sense. That's why we had a sample rate. That's just how often do we measure the position of this membrane. And the position of this membrane, we can have like 8 bits or maybe even 16 bits. That just determines the precision of the membrane position we get. So that's what a microphone does. Okay, so now what? Like, now I know this, but I have no idea how to turn these vibrations into something useful. And it turns out these positions are useless because when I make one sound, for example, a single sine wave, like there's a fixed vibration, but these positions are pretty useless because we want to know which tone it is. We want to know which frequency this signal actually is. We are not really interested in, well, now we're here, now it's there, now it's here. So we have to transform our data in some way. Because our ears and the microphone, they detect waves, but in your head, you hear a frequency. You don't hear the position of the wave, you hear some kind of frequency that's happening at that moment in time. So we need to transition from these waves into frequencies. If you have like a single sine wave, like I just said, then that's one frequency, and it's just that single frequency. If you have like a very short wave, it's a higher frequency. So in this case, it's a very low frequency. In this case, it's a very high frequency. So what happens if you combine these two frequencies? Like I can write code that detects a frequency like this. I can also write code that detects a frequency like this. This is something I can do. But if you combine two frequencies, then you get some weird looking thing like this. I cannot write code that transforms this weird graph into two distinct frequencies. I have no idea how to do that. And these values overlap. So how can I pull them back apart? No idea. So I did a little bit of Googling again, and it turns out you can use something like the Fourier transformation. And this actually helps you transform from the time domain, which is the positions, into the frequency domain, which are obviously the frequencies. So now I needed to know how the Fourier transformation works. There was a guy named Stuart Riffle, and he had a blog called All Dev Blog a Day, but his blog is no longer online. I could only find it using the Internet Archive, the Wayback Machine or something. So I cannot link to his blog, but I can re-explain how he explains the Fourier transformation in layman's terms. So if we have a particular noise, some recording we have this time and we have the position. And if we plot it like we did before, then we just go from right to left, and the position is plotted on the graph. So on the horizontal axis, there's time, and on the vertical axis, there's the position. What if the horizontal line is no longer time, but we just rotate it around? So we rotate this axis around, and we go, for example, like so. Instead, before we went like this. We went from on the horizontal axis with time, but now we are just rotating it. And how fast do we rotate it? Well, yeah, we can change that around. So let's, for example, rotate at a fixed frequency of 1 rotation per second. And you'll end up with some spirograph-like graph that you see here. But if we rotate now at a different frequency, if we rotate in a frequency that's actually present in the little recording we had, you'll see that it's being pulled off center. So if you would take an average of all the points in this line, you would see that it's no longer centered around the middle, but it's being pulled off center. And it turns out the more this frequency is present in the sample you have, the further it becomes away from the center point. So if we take our data, we turn this axis around and we record the average position, and we turn it around for each of the frequencies that we possibly want to know. And we record how far the average is from the center point. We know for each frequency how loud it is in the piece of information we just encoded. And if we would remove this frequency, it would instantly jump back to the middle. So next time you see a Fourier transformation and you see some complicated mathematical equation like this, it actually makes a lot of sense when you read it like this. So to find the energy x for some particular frequency, we spin, which is e to the I, which encodes spin, of your signal, which is xn, around a circle, 2 pi, a circle, makes sense, along k, that frequency we had, and then we average a bunch of points along that path. So even though it looks very complicated, we're just, instead of moving horizontally in the time axis and plotting the position of our microphone, we're just turning it around and we're looking at the average position. I kind of understand that. So I spent a couple of hours to investigate this, and now I know how to go from time to frequency domain. And then I decided to just use some built-in Fourier transformation because, yeah, that's who I am. I want to know how stuff works, but I don't actually want to write it because that's a lot of complicated code, and I don't know how to do that. So I used a library for that. There's one big problem. Like before in this graph, we have the time domain, and the horizontal axis had time. And we know at each particular moment in time, we know what's going on. But now we've turned this entire thing, we've removed time from the whole equation because we're now turning around on its own axis. And now we know something about the frequency in the entire song. But that's not very useful, because if you record 20 seconds of a song and then you do the Fourier transformation, and then you get as a result every frequency that was present in that 20-second sample, that's like playing all the instruments and singing all the words and tones at the same time. Like, that's not very useful. So we've lost time, like entirely. There's no more time component here. So I was getting a bit depressed. So it's almost time for dinner. And I was looking out of the window, and suddenly it hit me. Like a window, we can use windowing. So when we do windowing, we have this entire sample, and we just do the Fourier transformation on a little bit. This is enough to give us some frequency information. If you make the window too small, you can't do the entire circle thing. You just do half a circle. So that's not very useful. So the window has to have a certain size. But after that, we can just move over and do it for the next couple of milliseconds. And then we can move over and then do it for the next couple of milliseconds. So I wrote some code. The Fourier transformation works on complex numbers. So I take this entire byte array, then I slice it up into some slices, some fixed length slices of bytes. And for each slice, I do the Fourier transformation, and then I look at how far for each frequency it's off center. To improve this, I actually made a sliding window. I don't have the code here, but you can also do this using a sliding window where you don't slide it over entirely, but you just slide it over a little bit, and a little bit, and a little bit. And sure, you do have some overlap with the thing you've previously calculated, but this gives a lot of information about which frequencies are present, but also about which point in time these frequencies are actually happening. And in the end, it turns out I created this. You might ask, what is this? Well, it's written right there. It's a spectrum analyzer. So if I take this window and I move it over my sample, and for each window I take one vertical line, and in the bottom there are the low frequencies, and on top there are the high frequencies, and I record this. So let's do a small demo first. I can actually start this up. So in this case, I wrote a little program, and it's recording the microphone I'm currently talking in. And for each of the little slices, for each window, it plots the frequencies from low to high in time. So, and now I can say something like, hello. And here you can see the result. This is just random noise, but in the start, you can see it starts from low, and I went up in voice, and it ended up high. So this to me gave some good indication that my spectrogram was actually working. This actually encodes my microphone data into something with frequencies, low frequencies, high frequencies. So this was very useful for me. But I needed to know that it's actually properly working. So luckily, it turns out there's a song by Aphex Twin. Aphex Twin is a very experimental band. They make a lot of experimental music. But one of the things they like to do is that they like to hide images into their songs. So if you take a spectrogram of a song of theirs, then you can actually see an image in the song. So let's play a little bit from one of their songs, and you can actually see an image appear. Trigger warning, it's not really music. So that's what Aphex Twin calls music. To me, it sounds like a lot of noise, but you can see that in this particular ending of the song, they've actually hidden a face in there. So there's a human face hidden inside the music. And this this guy on YouTube used a very high-end spectrometer to analyze this, and he made this beautiful image. So I used my own code, which I just showed, with the same song, and I wanted to see the same image. And my image turned out something like this. This doesn't really look very well, but if you look closely, you can actually see the lines on the side. You can actually kind of see the head as well. So this to me gave me a very good idea that my microphone data was actually properly being transformed, and it actually made sense. So this was my first step of verification that what am I doing is actually working. So by then it was the end of Saturday. The weekend was halfway over, and I had a spectrogram. So not the thing I wanted to make, but it's the thing that I made. So a little recap. What did we learn today? Sound is actually made of small vibrations. A microphone and an ear are very similar. They detect these waves. Recording this sound in Java is actually surprisingly easy, just a couple lines of code. We learned the difference between sound in time domain and frequency domain. And we also learned that the Fourier transformation can be used to go from time domain into frequency domain. You can even, And you can also use windowing to take slices from your sample and move it over to get some idea of the timing back. So there's always a trade-off between how much time information do we have and how much frequency information do we get. But in my case, I just played around with it until it worked. There's no rules for it. I just played around until I thought it looked okay in the spectrogram. And the end was a working spectrum analyzer. Again, not what I wanted to make. I wanted to make Shazam, but I built a spectrum analyzer. But I still had a day left. So I went to sleep. And the following morning, I woke up early because I had no longer a hangover. And now I wanted to actually make something that I wanted to make. The final step is that we have fingerprinting. So if I use my microphone trash spectrometer thing and I listen to a song from Queen under pressure, I get this output. And if I do it again, I get this output. And you can see that both images look kind of similar. Like they're not the same, but they look rather similar. So instead of having a sound matching algorithm, I've now turned this into an image matching algorithm, basically. So what I decided to do, and this is kind of what Shazam also does, I found one of their research papers. They have a very complicated fingerprinting mechanism. So instead, I came up with my own little fingerprinting mechanism. I divided everything up in frequency bands. So a band for low frequency, a little bit higher frequencies until the highest frequencies. And for each of the slices I had, for each little window recording, I looked at in the frequency band, which was the loudest frequency there was. And this is what you just saw earlier. Instead of having all the blue dots, I'm now only looking at the loudest blue dots. So there can be a lot of background noise and background other people talking through your sample, for example. But we throw away a lot of data. And this is actually the key in this fingerprinting to make it efficient. We throw away a lot of data and we just focus on the main thing. So in this case, we have all these red dots. And if you would align it now, and overlay it, you can see that there's still differences, but sometimes it's very, very similar. So what I did next is I took one of these slices with the red dots, and there are a lot of frequencies, so I picked the loudest of these 8 bands we have, and then I compressed this down to just 64 bytes. And I stored this in a single long value of 64 bits. So as you can see, this slice we have, there's a couple of zeros first, and then there's 1, 1, 1, 1, with a 0 in between. And that corresponds to the red dot, and then the blue, and the red, and the blue, and the red, and the blue. So you can imagine that this entire thing we just had is just now a series of longs. Just a series of 64-bit values. And this is the fingerprint of the recording we made. So it's either from our microphone or it's from whatever is on your computer. So next I decided to create a library full of these fingerprints. So I used some Java libraries to process MP3 files. And after that, I just went through my entire MP3 library, which I had in 2010. You still had like MP3 libraries of everything you download. Now you just have Spotify. And for each of these MP3 files, I created this series of 64-bit values. Right now in Java, so this is Java 2010, then you need to write a lot of code. Right now you can just do this. Much easier. So what do we have now? I had about 3,000 MP3 songs, so I had 3,000 fingerprints. I've got a method to capture these fingerprints from the microphone as well, because if you do it from an MP3 file or from the bits from the microphone, it's exactly the same. Now I just need to match the long values that I get from the microphone against my entire database of fingerprints. So how does that work? because you can't, there's a lot of data there. You can't just match, go through and all the songs and look at all these particular bits and try to align all these images or something. We need a smarter way to do this. So our recording looks something like this. Now we can actually do a hash lookup in a table which has all the hashes of all our songs. And this is very fast. So for each 64-bit value, I do a single hash lookup. And there are maybe a dozen of songs that have this particular hash in them. And I write down which songs those are, and I write down what the offset is in the song. And if there are enough matches between what I have from my microphone and a particular song, then I just write down, this is a probable match. It turns out that fingerprinting is actually that easy. You just have these two sets of data. You do a hash lookup, which is very lossy. You throw away almost all the information. And then using these fingerprints, we do a lookup. And if it matches enough against a particular song at a particular point in time. So, for example, if I've got two different long values and it matches song A at point 105 and 617, but the other two sequential bits, long values, match song B at 613 and 614, then those offsets are actually the same. So they are the same distance in time as well, and that's what we record as a corresponding match. So we record the microphone, we've got all these bit values, then we do a hash lookup, and we just count the amount of hash hits we have. And just in time for dinner, I had my first working Shazam clone. And no kidding, I actually did this in the weekend, and it was, with all the learning, that easy. And now it's no longer magic. So I want to show you. So it's time for a small pop quiz. Right now, I've got this code here, which I can run. And you can see that it actually matches against the Rolling Stones magazine of 500 greatest songs. You can see that it actually loaded 483 songs because the MP3 library I downloaded with the 500 songs, 17 of those couldn't be opened or couldn't be processed or gave some error or something. And now I can actually take my phone here. I can fire up Spotify. You can see this is the Rolling Stone 500 greatest hits of all time playlist. And I can just try one of the songs. And you can see that it matches. So let's pick another random song. It still surprises me that it actually works so well. Like something I wrote in 2 days.
In America, you get food to eat.
Yeah.
Won't have to run to the... Just let me hear some of that rock and roll music.
Yeah, I hope you're all clapping now because I'm still amazed that it works this well. Like, I can't believe that it's actually so easy to make something like Shazam in a weekend. So let's quickly stop here, go back to the presentation, because there's even more. After I created this and I wrote a blog post about this and it went a little bit viral online, someone approached me and he asked me about, well, if you can match, and you just told me you've got the offset, would it be possible to actually say where in the song you are? Even better, his idea was, would it be possible for example, if you're in a movie theater, to know just by listening to the sound of the movie where you are in the movie. And this is the second thing I tried to create, and I actually sold it to him. I can't really tell you why he wanted this, but there's some use case for it. But I wrote an NDA, so I can't really explain this. But I actually made an alignment file. So in this case, when I start this program, it starts to listen for the movie Rush, the entire soundtrack. So right now it's listening to the movie Rush, to the entire soundtrack. If I open up YouTube, I can actually search for the movie Rush, and there are a lot of scenes online. So you can see that there are a couple of scenes from this Formula One movie. And if I pick one of these movies and it starts to play, it will recognize that it's actually from the movie, and it will actually recognize that the point in time where it is. And at that point, it will play back the same audio from the movie as the YouTube video has. At that point, I can stop the YouTube video, and my computer will keep on playing the soundtrack from the music, from the movie. And this actually, it works very fast. So let's quickly do some demo. Let's pick the first one.
Do you fly? No, I don't think that is sure.
And now I can stop this. And my computer keeps saying, well, this is 1 hour and 47 minutes into the movie. And it continues playing. So it knows where in this movie it is. And I can even pick, well, first I have to start the application again, of course. I can pick a different point in the movie. And now again, I can stop my phone because it recognized that this is 30 minutes and 2 minutes, 32 minutes into the movie. So this opens a whole lot of ideas or possibilities you could use it for. For example, one idea I had was maybe I can use this for an app that's on your phone. That, for example, there's a Dutch TV program called Wie is de Mol, which is all about secret hints and other stuff. What if the app is constantly listening to the actual TV program, and it can actually give certain hints in the app when the TV program is being broadcast? But it now even works if you record it later and watch it back. So it still works at any point in time. When it hears something that's happening on the TV, it can actually react to it. Another idea I had, at the time I had a big, my girlfriend, she liked Justin Bieber. I hated Justin Bieber. So what I did is I created a small app that every time it hears a song from Justin Bieber, it starts to shout, like just same song, but just. So these things, all these things are possible if you use this piece of code I just created. Anyway, let's go back to the presentation. So other ideas, how can you use this information? How can you use this technology? One thing I directly used it is to detect duplicate songs. So like I said, I had 3,000 songs in my MP3 library, and it instantly gave me back a couple of duplicates. Like, for example, certain songs that I also had a live album. And it was similar enough that it says, well, this live version and this song, it's actually the same song. So you could totally use this. Alignment of subtitles, for example. One really annoying thing is if you download a movie and you download the subtitles, that the subtitles and the movie, they're not in sync. If you have the subtitles react to the actual sound, then it doesn't matter if the movie it can no longer be misaligned because it reacts to the sound. Should totally work. I don't know why this hasn't been implemented yet. It can be used for copyright infringement. Something like this is something that Google, for example, is using on YouTube. if you use some song in your movie, in your recordings, then it can actually match it like this. Should totally work. Can you use this to do speech recognition? No, because it really has to match perfectly. So the frequency and the timing needs to be exactly the same. And in speech recognition, this is not the case. Everyone's voice is different, but sometimes you talk slow, sometimes you talk fast. So I don't think this can be used there. Yeah. So final recap of the second day. You can use fingerprinting to match. Hash lookups are incredibly fast. So even a company like Shazam, which does millions of songs, the reason they can do this so quickly is because of hash lookups. That's the whole trick here. It's very cool technology, but it's certainly not impossible for a regular programmer like me to create something like this. And my idea and my way of doing things and hacking it was incredibly simple. So there's lots of room for improvement. But yeah, I'll leave that up to an exercise for the reader. But I had my end goal. I knew how everything worked. I can explain it to you. And I had a working music matching algorithm thingy at the end of the weekend. That was a lot of information. So are there any questions?